We're going to take a look back in section 9.1 today, and we had taken a look a little bit at some properties of probability, and this was the screen that we had done last time, and some of this is going to come up into the next slide. So the next slide is actually a really good slide for us to start because it's going to be kind of like a summary of the slides before. There's a couple extra things in there that are new, but mostly a summary. So some things to remember when we were talking about probability is that we can talk about the probability of an event's empty set. Sorry, the probability of an empty set. That would be actually a zero probability. This would be the equivalent of, we talked about this, an impossible event. We took one of my daughter's friends with us to the lake this past weekend, and she asked me twice before we left Shawnee if we could go back to her house and get her swimming suit. Said, you are not going to need a swimming suit at the lake in March. 0% chance of that happening, right? We're not getting in the water in March. So this is an impossible event, the likelihood of something that's absolutely no way, shape, or form going to happen. You also have a probability of the entire sample space. This would be the number 1. This is what we call a certain event. Yes, this is an S for sample space. We had done S for sample space. Maybe it was in Math 1 where we used it, I don't remember. We talked about it last time as well, where we talked about listing out all of the different items in a collection of we did a dice problem where we rolled the dice and we wrote down all the possible outcomes. It's probability of the sample space, the entire sample space. So this is a certain event, something you know for sure is going to happen. And then for any other event, their probabilities are always going to be between 0 and 1. And we did talk about that last time. We talked about how you can't say that you're going to have a 110% chance of something happening. It doesn't really make sense. 100% means it's for sure going to happen. 0% means it for sure can't happen. So everything else should be somewhere in between. Those are percentages, but the probabilities are correlated to that, right? So if you have a 0.5 probability, that's a 50% chance. That's what you're looking at in those sense. All right, the next two came from different theorems that we'd had. So if A intersect B is the empty set, so two events that have nothing in common, then the probability of the intersection, the union is what I want there. The probability of the union is the probability of each of the individuals added together, each of the individual events added together. We talked about this when we were talking about rolling, and I don't remember specifically our numbers, but let's say we were doing that rolling the die. So what's the probability of rolling an even? Well, we could find the probability of rolling a 2, the probability of rolling a 3, and the probability of, a 4, and the probability of rolling a 6. And we could add those individual probabilities together, and that would be the same thing as adding sort of all the evens together and then writing that over 6. They're equivalent expressions for the same thing. Because you can't roll both a 2 and a 4 at the same time. Those are mutually exclusive events. We've talked about that last time as well. They have nothing in common. Can't both happen at the same time. Now, if you don't have that the case, that is, if you don't have this ability to say that they're distinguishable, that we can separate them, that they're non-empty, then in general, the probability of A union B is the probability of event A plus the probability of event B minus the probability of the intersection. Jot that down, and then I'm going to go backwards in our slideshow here and pick up something we did last time so you can remember when we did this. So the one that we did like this was with our die over here on the evens and the primes. So if we wanted to do the probability of rolling an even number, we talked about that being 3 out of 6. The probability of rolling a prime number was 3 out of 6. But if you want the probability of rolling an even or a prime, you can't just add 3 over 6 and 3 over 6 and get 1, right? Because something got double counted, yeah? The 2's. So we would have to remove that probability. Well, the probability of rolling a 2 is 1 out of 6. So then you could actually add 3 over 6 plus 3 over 6 and subtract 1 over 6, and we'd get the 5 over 6 that we would get if we just counted up the individual numbers in there that are distinctly different. That's what this is saying over here. And it's also important to realize that this is just a more general case of number 4. Notice on number 4, if you had the probability, or if you had the two values, they don't intersect at all, right? If that's equal to the empty set, then that means this is an impossible event. It can't be in both sets at the same time, right? So if you used this formula, what would this probability of A intersect B equal if they never intersect? 0, right? So this formula on number 5 actually turns into the same formula as number 4 when you look at the case where there's no intersection between sets. Okay, so it's just a more general case that actually covers that possibility as well. And then the last one talks about the probability of a complement. And the probability of a complement is 1 minus the probability of the set. And we had variations of this last time. We wrote down this, and we wrote down, we could say probability of A is 1 minus the probability of its complement, which is A complement, or we could write down that the probability of A plus the probability of A complement is equal to 1. And these are all it's just algebra. We're adding and subtracting things to each side. Okay, so I think we need some examples, don't you? We've talked about a lot of theory in this section so far. We've done very few examples. So we're going to do an example. We're going to do it with some cards. Now, I know that not everybody is as familiar as others with playing cards, so I want to start by talking a little bit through playing cards because you're seeing an example in your notes, your homework from this perspective too. So let's run through a few things. So what colors are there in a standard deck of cards? Red and black. How many cards are there total? 52. How many red? 26. How many black? 26. Good. And let's do suits. What are the suits in a deck of cards? Hearts, spades, diamonds, and clubs, right? So which ones are black? Clubs and spades. And which ones are red? Diamonds, and hearts. Very good. How many are there of each suit? 13, right? So, and if you're just like trying to feverishly write this down, you're welcome to come talk with me about these later if you're not familiar enough with them to actually remember these details. Let's talk about the actual face values of the cards. That is what appears on the cards themselves. So we have some of them that are number cards. What are the number cards? What's the smallest? 2, good, and the largest is 10. All right, so we have number cards that go from 2 to 10 in each suit. What else do we have? We have some face cards. What are my face cards? King, queen, and jack. And that's how your book's going to call it too. So it's not going to say that ace is a face card or a number card. So ace is an otherwise kind of card. And we kind of treat it that way in some games. Sometimes you play ace low, and it's a low value like a number 1, and sometimes you play ace high, and it's a high value, like being better than a king. So it just depends on the game you're playing. Try to think if that's all we need. I think that might be it for now. So let's do this question, and if we run into any other questions that I haven't dealt with the issues, we'll deal with them then. All right, we've got a single card that we're going to select from a standard deck of cards, 52 cards, right? And we're going to determine which of the following are equally likely. Now, if we're only asked whether they're equally likely, we're not actually asked to find the probabilities. But we're going to justify why we're making the statement that they are or they are not equally likely. Does that make sense? So it's sort of inherent in how the problem is asked that we have to at least assess what the probability is, or at least what it could reasonably look like. So let's talk about our face cards. So how many face cards are there in a deck? 12. So there's 3. There's the king, the queen, the jack of each of the suits, right? And so we have 3 then times 4. So there's 12 face cards out of how many cards total? 52. So this is a 12 out of 52 chance that you draw a face card. Right? That would be the probability of drawing a face card. What about something that's not a face card? Bigger. 40. Yeah. There are 40 cards that are not face cards. Now, there's several ways that you could do that. You could literally count them up. What else could you do that would make it quicker? Yeah, we could subtract the 12 from the 52. So if we've got face card, not a face card, well, there's 52 cards. So 52 minus the 12 would give me the 40. So the face cards, the probability of drawing one of those is 12 out of 52. The probability of drawing something that's not a face card is 40 out of 52. So are these events equally likely? No, because the probabilities don't match. If the probabilities were the same, then yes, they would be equally likely. Now we could also actually, if we were asked to find these individual probabilities, we wouldn't leave them as 40 out of 52, right? We would reduce them, just like you did back in our section on fractions, right? Yes, so I'm not trying to argue that this is an answer to that part. The answer to the question is actually no, they're not equally likely. The justification for it is that we found probabilities that didn't match. All right, how about clubs? How likely are you to draw clubs? 13 out of 52, because there's 13 clubs, 52 cards. What about diamonds? Mm-hmm. Hearts? And spades? Are these events equally likely? Yes, they are. Probabilities match. Good. How about the probability of drawing a black card?
26.
26 out of 52. Red?
26.
And are these events equally likely? Yes. All right, how about the last one? How about the probability of drawing a king? 4 out of 52. Queen? Jack? Ace? Another 4 out of 52. Okay, so now if the problem stopped there, would the events be equally likely?
Yes.
Yes, but we've got a couple more events. And the next one is even card. How many even cards are there? Write it down.
25.
So how many? 20. There are 20 even cards out of 52, right? How many odd cards are there?
Does ace count?
No, ace doesn't count as odd. It doesn't have a number value. So there are 16. There are fewer odd cards than there are even cards. 16 out of 52. So are these events, there are 6 events there, equally likely?
No.
No. All right, so do we have the idea of how to answer those kind of questions? Okay, great. All right, let's do one that's a little different. A civ class is composed of 21 men, 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 3 math majors, and 5 English majors. The next statement actually really is important, although it doesn't look like it maybe is at the outset. It says, assuming that no one has a double major, if a single student is chosen at random, what's the probability that they are the following? So why does it matter that we say that there's no double majors? Yeah. So if we had, for instance, someone who was an English and a religion major, if they had both of those, then the problem would be that we couldn't sort of say, oh, there's 13 of these and there's 5 of these, so there's 18 total people, right? Because somebody would have been counted in both of those lists. So the fact that there's no double majors is a really helpful piece of information that allows us to know that we're not going to have double counts. All right, so let's start with female. What's the probability that if we select a student at random that they're female? Right, so there's 34 females, and out of what was it, did you say? 55. So where'd you get 55? Right. So the 21 and the 34 gives us 55 people in the class. Now, 34 and 55, do they have anything in common to reduce? They don't. 55 is only divisible by 5 and 11, right? And neither of those divides the 34. So we're good to stop there. How about a science major? 12 out of 55. Can we reduce that one? Nope. All right, now we actually have the English or religion that I was mentioning before. An English major or a religion major. And it matters, again, right, that there's no double counting. So how many English or religion majors do we have? There are 18 out of the 55. And does that one reduce? No. Evidently, I didn't choose very fun numbers since they don't reduce, huh? Now this one says neither a math major nor a science major. There's 2 different ways we could do this problem. So somebody give me a suggestion. Right. So we could add the math and we could add the science. Let's see, what was the math? 3. There it is. 3 math, 12 science. So how many math or science are there? 15. So if it was math or science, we could actually have 15 that are math or science. So how many are not math or science? 40. Okay, so one way to do this then would be to do that with sort of a subtraction. That would be 40 out of 55. And believe it or not, you're using a probability theorem when you did that. You didn't use it directly, but the theorem that you used is this last one over here. You actually found the number of people that were not math or science by finding the number of people who were and subtracting it from 100%, which was the 55 total people. This is the theorem that you were using by default. Now, you don't have to do this way. What's the other way you could do it instead of, I know we're not done with it, we need to reduce it, but what's the other way that you could do this particular problem? We could add up all the other majors, right? So we could add up the 22 education, the 13 religion, and the 5 English. And on this particular problem, that's really not much different than what we did, right? It's pretty much the same number of steps even. We do need to reduce this one because it actually does reduce to what? 8 out of 11. Any questions on that one? All right. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What's your reply? There's several things that we need to hit on here. So somebody give me one issue of what their reasoning is. That's a very good point, Lydia. So one issue that they have here, we'll just kind of star it or bullet it or whatever, is that these events are what we call independent. They do not have any effect on one another. Right? The first flip has no bearing on what happens in the second flip. This is the reason some people can have like 7 daughters and no boys. Right? Every child has an individual chance of having that Y chromosome or whatever, right? They're independent events. There's another issue in their reasoning. Yes, and that has to do with the fact that they're independent. So the probability, I'll write that down, but that's related to the first idea, Abby. The probability of, what was it, heads? Tails. The probability of tails is always 1/2. It's a 50-50 chance. There's something else here that should be bothersome to you. I mean, let's say that somehow these events weren't independent. Somehow they affected one another. There's still a problem with this student's reasoning.
If it kept going to heads, you assume, well, then it's probably going to keep going to heads because it's already happened that many times. Like, obviously, something's causing it to run on heads.
You might sort of, like that there's an unequal sort of a weighting maybe on the coin or something like that. That's true. Not quite what I'm going for there, Lydia. There's something else here. I'm sure you guys are just reading right over it. Read the problem carefully. What is weird about the 5 times, Angela?
Well, because two, like, if they got it equally, you could have, or not necessarily equally, you could have 2 heads and 3 tails.
Not quite, although that's an interesting point that if we had an odd number of rolls, that we would obviously have to have one more than the other, for sure. Not still where we're headed.
They could have flipped and got tails before they had the 5 heads in a row.
Could have, so we don't know what happened before those 5 flips. This phrase should bother you with a student's argument. We talked about this last time. Let me see where it was. Oh, there it was. The law of large numbers, Bernoulli's theorem, says that if an experiment is repeated a large number of times, the probability approaches a fixed number. But even without knowing that, that phrase in this problem should bother you with the student's argument. Why? It's not a large number. The student's trying to make a claim about law of large numbers, and they don't even have a large number. Like if they did this 5 million times, 5,000 times, we might have a discussion about this being a large number. But this isn't even a large number. This has not happened a whole bunch of times, right? So this issue as well is present there, is that 5 is not a large number. So even if there was some sort of a way that the other 2 issues above here, and some of the others that you guys mentioned as well, weren't going on, we couldn't make this claim about the number 5 because 5 isn't a large number to start with. Does that make sense? Okay. So lots of weird things going on. How about this one? This is an interesting one. The following spinner is spun 100 times. Joe claims that the number 4 should occur or will occur most often because the greatest area of the spinner is covered by the number 4. What would you tell Joe about his conjecture? That little red piece right there is the spinner. That's what's going around. And what is the probability that 4 will occur on any spin? So what do you think?
They each have the same angle.
Ah, it's not about the area, right? So the spinner doesn't spin through area. Do you guys follow what I'm saying with that? The spinner spins through an angle. And all 4 of these angles are equal. So what is the probability of spinning a 4? It's 1 out of 4 because there are 4 equally measured angles. They're all right angles in this particular problem. Now let me change the problem slightly, and I want you to think, what if you had this same spinner, blown up big or whatever, put on the wall, and you were throwing darts at it? Then it would matter, wouldn't it? Then would you be more likely to get a 4?
Yeah.
Absolutely. So don't let the picture dictate what you're talking about. You really have to talk about what is it the probability of happening. In this case, it was a spinner. In my verbal example, it was an example of darts. That's a different case, okay? Same picture, though. We can talk about it in a very different way. All right.